Okay, we're live. We are live. Hello and welcome back to Old School Coding, where I'm using the techniques of the early 90s in a programming language from the early 90s to design a simulator for a computer system that might have existed in the 90s. Whether we actually get something that is accurate to an actual system in the 90s is something we are striving for, but we'll probably finagle some things, sweep some details under the rug. I'm trying to do signal accurate, which means I'm not just doing an instruction set thingy. I'm trying to actually model the traces you would see on logic analyzer or on an oscilloscope as you poked around inside a MSI 8080 or an Altair 8800 or a Sol 20 or whatever the Intel MDS 80 you might have had on hand. As a hobbyist, I had access to a number of different computers at various times in my life. Obviously, the really expensive ones that would only appear at major corporations were something I didn't get to touch until much later. But certainly, I was able to interact with Apples and TRS-80s and MSIs and Altairs and so on. Even had a Sol of my own. Anyway, so we are working our way through all of the instructions of the 8080, trying to hook that up into our 8080 simulation. And I've gotten to the point now where I think my next thing I want to tackle is this second line right here, where we are moving data from an address in memory. So HL, the HL register pair has a memory address in it. We want to go get the data from that cell of memory and toss it into a register. And the line after that, which is very similar, take the value from a register and put it in that cell. So let's do the first one first, which is essentially a store register to M. The layout of that on the cycles, during the machine cycle 1, we have a do nothing in T4, and there's a footnote 3 on that. This says states T4 and T5 are present as required for operations that are not, which are completely internal to the CPU. So this says, that's actually a footnote for all of them, but this is the first one in the table. Basically, it's the X stuff that we've been doing that says we're doing nothing during T4. We've already done instruction decode, and now we're just kind of dispatching out, and this cycle is taken up by the hardware to finish up its instruction decode. And we are sending ourselves to a next machine cycle, which is going to be reading memory at HL with a sweep up here in M2T3 that writes it to the selected register. Pretty simple. And I'm going to put that in the same file where we did the other move registers. Just, it's sort of related. I know. Let's turn off the PDF, get it out of the way. Okay, so we want to go down to the MOV thing here. We already have all of these things, including a T5 here, which moves something into the register. In the T5, if we go down and look at it, this guy says, basically, we're taking the whatever in TMP, and we're moving it into R. Well, it's going to be a little bit different for the move M instructions. Okay, so the M1T4 is going to be common for all of these. There's a destination register, so this is MOV R, M. For each destination register, the opcode for this is 01, the top 2 bits, followed by the destination register left shifted by 3, followed by a 6. So 04. This is octal 0100, by the way. I used to think in octal, Now I'm not so sure. So it's really the same opcode, just with a source register of 6. Well, it turns out that is just this guy right here. Let's see here. Now, I don't want to start manipulating my inits to compress them at the expense of making them less easy to maintain. So this is MOV R1, R2. Also, I don't want to accidentally try to encode a MOV M, M, which is actually just the halt instruction. So for this guy right here, which is MOV from M into destination register, M1T4 is going to be a X cycle, which is going to dump us into a read M. So this is I8080 underscore state underscore what? MOV DM T4. I'll just call it MOV that. MOV destination register from M. And that means I need to declare these two functions. And we also have MOV MD, MS T4. I'm going to kind of do the two directions of the move in parallel. And then we have a data bus that goes to temp. Actually, MOV MS, this is going to be a separate one for each register. MOV M R T4. Which means we need to do this as a macro. This is a M1T4 for, we need to rename these. No, we're not. We're going to keep these names for the stock move. I will name RM. Doesn't require a macro. MOV MS does require a macro. Now, let's call it MOV T4M. So WR for write memory and RD for read memory. So referring to the PDF, getting down to the nitty-gritty, I always have to double check this stuff. The only time the register comes in is here out in M2T3. So MOV RD, comma M, common code out until M2T3, which moves data to R. MOV M, RS, M1T4, copies R to temp, then common code to move temp to HL. So this guy, we don't need to have a macro until M2T3. And this is M1T4, which is different. So we have MOV T4 RD. M2T1 read, M2T2 read, M2TW read. Yeah, because we can have wait states, remember? When T1, that will send the HL registers to the address and send status. This switches over to sending, to receiving the data, wait for the data, and then we have a T state that dives us into here. M1T4 copies R to temp, and then we have another set of these. And we haven't yet worked out how wait states would work on a write. I believe that in the hardware, it is just a direct analog of the read, where we initially have the address goes out, and in the actual hardware, we get the memory read and memory write signals going. And the remote guy would say, oh, I'm not ready. And eventually you would come ready, and you would get either a read or a write strobe, which would then do the data. If we want to do wait states on writes in the simulation, I will have to go back and revisit all of the bits of code that do it, and that's going to be a pain in the butt, and I anticipate from that we will not make the decision to allow wait states on writes. We will simply say, our remote guys are just going to have to capture the data and deal with it. My mouse cursor. There we are. So those are the various things we need. I'm going to copy these. Well, first of all, let's lace them into their proper places. So MOV RM, this is a read. So this is actually pulling up MOV T4 read for M1T4. Okay. Then we have MOV M, R. Let's call this RD RS. And this is a macro, so we need a table. There. This is name. We're going to change M1T5 to WR M1T4 like that. So we now have a whole bunch of things that are undeclared. Get expansion here. There's our declarations. Okay. Used but never defined, yada yada. Declared static but never defined, yada yada. Warning used but never defined. All these things that we haven't defined yet are all like that. So now we grab all of this. We go down to the bottom of the file to do the implementation. I'm going to do a keyboard macro to take care of this stuff. Static void that with parameters. Okay, that should have fewer warnings. And let's trim those down to just that. And these are all the names that are defined in macros. And we have a bunch of things defined and not used yet. That's cool. So this is this name. Filled in with various R's. E, C, D, E, H, L, A. And I think this is fewer messages, but we still have a whole bunch of them. So now we do this bottom guy. Think B C D E H L A. So now we have a whole bunch of defined and not used. So at this point, we already have a problem here where we are overwriting something. Because we overwrote halt right here. If DDD is equal to 6, I'm going to make this explicit. And we no longer need that temp. We have just the warnings now, defined and not used. So now we need to go down and set these functions up so that they all step to the next guy. I'm going to do one of them as just as a template and then fill in the rest. So let's start off with this thing right here, this switch. And I'm going to just put empty switch in each one of these with a thingy at the bottom to set state next to some TBD value. In fact, what I'm going to do is I'm going to set this to 0. And I'm going to include, no, I'm not. Okay, so this switch gets substituted in for all of these guys. So we're going to change that to that. So it's a sequence here. MOV M4, MOV T4RD is going to set up to go to this guy. Oops. And this goes onward to M2 T2 read, M2 T2 read goes either to T3 read or TW read. And here's our logic. Well, T3 read is not T3 read, it's T3 read R. Which is in a table somewhere, is it not? This needs to be in the CPU stuff. And we are redispatching because it's all common code. So this is CPU arrow M2 T3 of CPU arrow IR data. Oops. Value. Now we need to set this for the read stuff. Well, wait a minute. This function here, we're trying to hook up an M2T3, is literally a move from the data bus to the register. So this is very much like an existing one that moves into a register. It is very much like this M1T4 of the register here. It's T5. Not the same because it's reading from temp, so we can't actually use these functions. But we can make M1T5 like this. M1T5 becomes WR underscore M2T3. So there's the name. Oops. We got the name. Let's put the defen up there. And that's the wrong one. Data definition has storage or there we go. This is name RD M2T3. So back to linking up all of these little functions. So we got the first few. So down through here, and this dives through M2T3. This gets into one of these registers. Now these are all the same code, but writing into a different register, which means these need to be a macro. We have the same problem with the indenter that we had before. That for some reason, this is simple enough. The indenter is handling it, but that's not in general true. Do I have a decal? No. Okay, so during this, we can wipe out the rest of these. LA. This is the final cycle of the transfer. We are going to move from the data bus to the register R. So this is data to CPU arrow R is CPU arrow data. And there's other things we have to do because we are closing off a memory read. Let's go to 2bops and take a look at that. Oh, that's right. We don't have the T3 here. We have to go to somebody that uses 2bops. How about an MVI? So things that we do, we move from data, and then we release DB in and tri-state the address bus. And state next is not set to anything because we're using red M1 int, just like that. Now this is not going to compile properly because R but we can turn it into a macro properly. Okay. Why? Try this one more time. Indented properly. Give it an extra blank at the beginning. Put the backslashes on. And then we need an extra extern definition for this to have a semicolon after the thing. Let's copy this comment. And this is defin RD is what I'm using to disambiguate here. And back up. Get the indenting. There we go. So that should handle all of the T3 read stuff. So we want to do something similar. M2T3 becomes WR M1T4. And what do we do here? This is much like a 8080 2bops. We are going to start right in with the T1 work. So here, we're going to have to deal with this as a function first. Don't know why I did that the long way. So during T1, phi2 rise gets the address. This is HL, so H var arrow value right shift left shifted by 8, or CPU arrow L arrow value, and it's C. Boom. And this is a memory read from HL, and we assert sync. And the next thing we want to do after all of these, that's not correct. This isn't a T1. Okay. Back to doing the right thing. So during M1T4, we're moving our source register into the temp register, and then we are going to head off to the next guy. So this is data 2 of CPU arrow temp, CPU arrow R arrow value. And state next heads into our shared thing. Once we've moved stuff from the register we care about, the rest of this is all common. And the next one we want to go through is T1WR. Start keyboard macro. End of line, 1 blank, backslash, next line. Okay, now, start keyboard macro, tab, next line, so we get all the backslashes lined up. There we go. So that defines all of these guys, and now I'm going to go wipe out these individual definitions. And the one thing that I forgot to do is actually to call this macro here, and oops. That, and like that. Oh, semicolons at the end. And this is WR M1T4. So here, oops, there we go. So work my way down, work my way up. Okay, so this is defined and not used because we never get to it. Her, that's because this moves to this guy. And the final guy needs to ret M1 int. So what do we do during T1 and T2 of M2 here? Oh, and T3. So we have 3 T states for the write register to memory. Our data is in temp, so phi2 rise. This is a memory write cycle, so we are sending HL out with our status. What status did we set here? M2T1 needs to start a sync. In fact, all of this stuff is unimplemented yet. So M1 here's where we're starting our work. So make sure we are implementing. So this is M1T4. Does nothing, but send us to this T1. This T1 needs to start doing real work. And that real work is going to be a read of memory at HL. Where did I do that? Here. Start the read there. Then in the T2 cycle, normally we would increment the PC, which we are not doing here. We release data, release sync, raise dbn. Then we have a T-wait cycle, which asserts wait. And reasserts dbn. Let's make sure we hook all this up. And that means that in the T3 cycle, we also need edge low CPU wait. Okay. So M1T4, we move our R value into temp and head on into here. This is going to initiate a memory read cycle, or memory write cycle, sorry, which looks a lot like the other one. In fact, let's put them side by side. So M2T1 for read goes there. M2T1 for write goes there. And I guess I can remove these comments. So we set our register, our address into IDAL. We copy it into the address word. We set this to status mWrite. And we start a sync. In phi2 down here, we release sync. Now, I did do something different for the write cycles, didn't I? Yes, I did. We were going to edge low WR and then phi2 fall, we're going to put it high again. So let's look at I8080 MOV in-out.c, where we actually do a write cycle. I'm going to make it look the same. So here, while we're doing an output, we do send the data during phi2 rising, which is correct. We don't data Z, we do data 2, and it is in the temp register. Whoops, wrong place. No, T2W, that's correct. So during T2, phi2 rising, we start sending the data. During T3, phi1 rising, we assert write, and normally write would go low on the next phi1 rising. We're dropping it early. So red M1 int, write, and we're setting that high, and we also want to release the address bus here. Okay, so what do we have now? I-8080 state MOV M2T3WR. Was not declared. We do need it. Okay, we're now compiling. We're not actually executing any of this yet. But there we go. More coffee, more code. So, well, we got this. All these MOVs, now we can move to and from the M register. Let's take a look at what we need to do in our test to fix that. So this is still using these fragments here. To test M, I need to have control over H and L, so this is going to be a slightly different program called mem program. Oh, let's now memory test of R M comma RS and MOV M comma RD comma M. So we have a problem. We cannot test reading from memory properly with shadow in place. So I can't do a write of a data to memory and then read it back and get the right thing. What I can do is read from M register, which points at the ROM stuff. Okay. And then I can write it to RAM, and then I can check the RAM. So we're going to do basically a, let's set this up as a I-8080 MOV-M test. It's a separate test thing. And what I'm going to do is I'm going to write some assembly code. So we have here things like jump test, MOV-M test.asm. This test is being used before we deal with shadow, so it can only read the shadow ROM. And writes will go, oh, come on, to the shadowed RAM area. So I'm going to do LXI HL, comma, start. And we are going to be using a bunch of things. So we are then going to say LXI, let's see, how do we want to do this? I'm going to copy 256 bytes. Well, no, I'm not. I'm going to copy some number of bytes. MOV C is going to be my count. And we're going to say end, start. And I will have to have it end down here, where I'm going to put a halt instruction. Actually, no, I'll put, yeah. So we're going to copy into RAM up through, but not including the halt instruction. So we're going to move from M to the B register. And we'll move back to M from the B register. Like that. Now, we actually want to hook into this subtest thingy. I don't think I want to plot this if I do so many of them. Let's just move 4 bytes, okay? And what I will do is, at the top of the loop, I'm going to do RST2. So we're going to start a new plot at the top of every loop. And it's going to go down through the JMZ. At the bottom, we're going to do an RST1 for we are done. And that we use the same RST stuff. I need to get away from using RST because I'm not going to be able to do that. Let's start thinking here. What I want to do is use some illegal instructions. So all these places I've used RST, I'm going to change to using illegal instructions. But not right now. I'll do that as a separate refactoring stage. So here's our program. LST. This should give me MOV test. Bad source registers, so 4, this would be MVI. Okay, so we're going to loop through this. Eventually, we'll set this to end minus start and copy the whole thing. Now, our test on the other end will have to run this, and then at the end, we'll have to check the contents of RAM and make sure that we copied exactly 4 bytes, no more, no less. So source test I8080 MOVM test.c. Start off with MOV test to get some of the stuff. I8080 MOVM is going to be test the M, RS and MOV RD, M instructions. Now the downside of this is we're only testing the B register. But I think Let's test 2 registers. Let's use D and E. So test D and E as the 2 registers are moving through. We're not going to be testing MOV and from. This is a test. Okay, A. B, B. We don't want to move through C because, let's not do this with the loop. C, C, D, E. Moving from H and L is not a good idea. A, B, C, D, E. I think if all 5 of those are working, I can assume the other 3 are working. Well, the other 2 are working. We're not going to do that. Let's do a plot for each one of those. And just for fun, I'm going to say MVI so if this doesn't actually write the B register, we're going to come up with something. So what is my error? Oh, right. I constructed this guy, and I didn't do anything with it. MOV post. Gonna gut all of these and replace them with code from the bit of code that uses the assembly code to test. So it's MOV test. Run the test program in test.hex, then compare, then check that RAM has been updated. The 5 bytes are copied from ROM to RAM. So what was my latest one to do this? I believe that the I/O test was probably my best one so far. Let's go down to its BIST and take a look. Okay. We're going to copy a bunch of stuff in and delete a bunch more stuff. So tau, we're going to need RAM as well. This is RAM 8107X8. X4 is going to be the RAM array. We don't care about PC. We do not have a test thingy. We don't have a dev. We do need to no test dev. We're going to assert that the PC is starting at 0 when we get to here. We're doing the same overloading we were doing before. This is all part of the support thing that I will be lifting out. So, support code. There's our boilerplate. Again, that will all go into a common please run this test program. Test done, test page, page number, load that up, and start T0 for the first plot. And I guess I can just grab the rest of that. Okay. Oh, I do use PC. Of course I do, but that's the only place I use it. We do not do trace TD. So all the trace TD stuff is going to go away. We're not doing anything with RAM yet or decoder. We don't need decoder. So here we load the ROM. And what I then want to do is set the RAM to a known pattern. We use memset for that. RAM sub 0, well, we don't want to RAM do that. What we want to do is we want to go into RAM 8107 and pull out the cell array. So RAM sub 0 is going to be one of these guys, arrow cells. We want to set it to a character, which is 0xAA. Actually, let's go do 5A. And the number of cells we want to do is, let's do 256 bytes. So now we have to do all of these, which are just going to be the same thing, changing underscore IO to underscore MOVM. Hey, how about that? And that actually did something, except that, of course, we're not calling these guys. So if I put in print top and print end, we will see that we are not actually getting into these functions yet. To do check contents of RAM. Come on, dash greater than cells. So we're not being called yet. So now we go to i8080 test.c. I'm going to run the MOV test way down here. Okay, so they're not declared. So what we're going to do is we're going to search for _IO_, duplicate the line, search for IO, and change it to MOVM, like that. And now we are getting into our tests. So I can delete those lines. Let's just do the first 16 bytes. So we can see here that the RAM is now starting off with the first 5 bytes identical. 1, 2, 3, 4, 5. Yep. Okay. 210000 3E55, and then the rest of it is uninitialized. So this is correct. And I just need to put in tests for that. 0 less than 5. Actually, let's do less than 256. If I is less than 5, else assert EQ integer. My expected value is ROM sub 0 and row cells I and RAM sub 0. And this is going to be RAM area. Lucy wants to review my work. Time for code review, Lucy. I haven't even put in a PR yet, and she already wants to review this. Okay, so let's take a look at what we've got here. Oh, good Lord, I have been coding behind the PDF all this time. Oh, I am so sorry. So, we really do have to review this. I have no idea how much of this is. Oh, good Lord. She's not happy with me. So, we've got our test code on the left, our real code on the right. Now, just in case I obscured this whole thing, here's how it goes down. We have added the following sequence of states for the memory read operation and the memory write operation. We've got a T4 that says we're going to read. We've got a second machine cycle, T1, T2, T wait, which initiate the read from M. And then we have a separate little handler function for each register we're reading into. And this final register reader is going to then yank on the return to M1 and we're done. For the other direction, during M1 T4, we have a different handler for each register to move the register value into the temp register, the temp latch. And then we've got a second machine cycle, which is common to everything, which basically initiates a write cycle to memory and sends the temp register out. So those are our declarations. That's the functions that we're going to have. We added in definitions for them all, and we added in a couple of tables so that we could pick out the right ones. During initialization, we are writing M1T4 tables for them all, and for the read, we have to update the M2 T3 table, so we get control back during the T3 cycle of the M2 machine cycle, so T3 state of the M2 cycle, to route our data to the appropriate register. So implementation. So the memory read operation, oops, this is memory write. Yes, okay, so doing memory write first. Oh, this is the implementation of MOV. Let's go down to our new stuff. So memory read operation, which is what I was expecting to see next. During T4 of the instruction fetch, we really do nothing but finish up our decoding. And then we have the read cycle where we are forming the address, setting out IDAL, copy IDAL to the address bus, tell the data bus that we're status mread, and hit sync. So the rest of the system will know that this is a memory read machine cycle. And then we pass on to T2 state. During T2, we release the data bus, drop sync, and raise dbn. The more I think about this, the more I think that I should really be releasing the data bus after I drop sync, because data should remain valid through the end of sync. And while these are happening at the same time, quote unquote, it's not quite correct. Hey, Lucy, remind me to fix that. That's going to be everywhere that we manipulate the sync. We're going to need to move the data dropped after it. And once we have released those two, then we can raise dbin to say, hey, start sending your data to me. And when phi2 fall happens, we can then say check ready, and then either go into a wait state or dispatch to the proper T3 state handler for machine cycle 2. If we're in a wait state, we assert wait. We send another other rising edge on DB in so that people can know to wake up and think about whether they're ready or not. And again, the same test at the end in Phi2 falling. So once we get through there, we now have a separate function for each of these 7 destinations. And basically that says, okay, during Phi1, we release wait, and we assert the return to M1 signal internally, which says this is a final T state of an instruction. Now, this not only gets us to go back to M1 T1, this also folds into how we're going to handle interrupts. The interrupt input is gated on that. Instantiate that for each register. Now, this is M1 T4 of what? Hold on. Right, okay. So that is the read memory into register. Now we're going to write register into memory. So we start back in T4 again. And our job during T4 is to grab the register value that we want to send to memory, and we latch it into the temp latch, which we can then use for all of our operations. We move onward to common code. So once we've grabbed the value from the register, we now have one set of code for all of the source registers, and that is a M2 machine cycle, where again we use HL as the address. We use status mWrite, so we are sending data to memory, and we hit sync. And we come down here and we release sync, and we push our data from temp register onto the data bus. And during the T3 state, we assert the write signal, and again we hit return to M1. And at the end of this state, we're going to release the address bus and release the write signal, and we're done. So that is proper and correct here. Now let's take a look at the tests. Again, I was coding this behind the PDF for who knows how long. I'm not sure how much, if any, of this you saw. This is a copy of the I/O test with some things removed. The I/O test had a device that it created. We no longer create the device, but we do keep the rest of this. We will need RAM and ROM. And here's our plot data. So here's the stuff that will be made into a common service, where we are picking 3 instructions to divert. The common service is going to pick 3 illegal instructions to divert. Okay? Is that right, Lucy? Yeah. So we pick 3 instructions to divert, and we save off their original values, and we divert them to the support code. We're loading up our test program. We are setting some ROM to an initial value. When a real system comes out of reset, its memory will be in the same state it was in when you went into reset, which means if you are doing a power up, the state of the memory will be dependent upon what kind of chips you're using. Okay? If you're using DRAMs or static RAMs that are on initial power up, they may have a specific pattern that they start at. DRAMs will likely be in the state that they're in if you don't do refreshes, which may be all bits high. If for some reason you are simulating a truly old system that has magnetic core memory, then your core memory will be retaining whatever state it was in when you last turned off the machine, which is really kind of cool. I wonder if I can get enough information on even older machines so that we could simulate a machine that actually has core memory. It would be kind of fun. We would learn a lot about really, really old architectures. So maybe the point of this channel is going to be to start from the 8080 and move back in time. Does that sound like a good idea, Lucy? She's telling me I'm crazy. There's no way there's enough information about older machines to do that. So once we're here, we have this same loop that we had in the other test where we run the clock one step, and then we deal with, are we doing a test page? one step at a time. We're not going to step by instructions, because if we ever hit a halt instruction, the support for instruction would never return. So the clock one, at least if we hit a halt instruction, we're going to come back to our calling code here and have a shot at doing something. So, for example, we could have a counter. If this test ever runs well, we could put a counter in here that says, if you loop more than n times, bail. Fail and bail. So this is all boilerplate for run a program until you get to an RST2, or, well, any one of these RSTs that is a terminal state, which I believe is RST. Well, we'll see in a moment. We assert that we're done, and now this particular test wants to check the contents of the RAM cells. This needs to go away. And here we are saying the result of our program should be that the first 5 bytes of ROM are copied into RAM. So the RAM cells should have the ROM value. And above that, they should have the start value we put in. So there's our test completely written and working. So this should have created some plots in I-8080 MOV-M underscore whatever. Let's see if I can do this with the cat on my left. The cat is still nestled on my arm below the level of the camera. You can't see her, but there she is. So doc IMG Now, we only generate these plots if they're missing, so they may not be correct. I'm going to delete them. So we can assure that we have regenerated them. I'm going to rerun the reporting mechanism to regenerate them. Oh, and we're down to 66 unimplemented instruction codes. So let's get rid of this. I like to widen this area out when I start looking at these pictures. So here's the MOV-M page 1. And let's see, what have we got here? We have an instruction here. This is the LXI into HL, so we get L gets 0, and then H gets 0 here, and 3E, 7E, 7723. I need to get my assembly code source going here so I can follow along. LST. We're going into MOV-M test here. So first instruction is this guy, which sets HL. Then we set the accumulator to 5.5. And then we MOV A, M, which is going to take 2 cycles. What is going on here? Oh, this is a write. Okay. Scale on this is narrower than I expected. Are you ready to get down? Yeah, she doesn't look at plots. There you go. So we can look at our PC here to see our progress. MOV, LXI, H and L, L and then H. Then we have 3 and 4. These two together are the move immediate of 5.5 into the accumulator, which lands here. Remember, some of that stuff doesn't land until the T2 state of the next instruction. Then at 5, we have move A comma M. So this is going to set up for a read of memory, and we have address 6. The PC is address 6. If we look at the address bus, you'll notice the address bus here, we had a 5 for the fetch, and then we are reading memory here at 0. And if we scan down carefully, we can see the data bus input goes high. We can see a wait state, and we can see the data coming through. And we do indeed get this 2-1, which is our first data byte, which is at 0. So this is coming in, and now 2-1 appears in the accumulator. So this is the plot that correctly shows these first instructions. And then at location 8, we get the RST2, which is causing us to produce the plot. Plot number 2 will be very similar. It's going to move 5-5 into the B register here. And then it's going to move memory into the B register, and that's going to be a 0 from location 1. So here's our address bus, which is from HL. And we're going to move that back out to address 1. Now this read from address 1 is going to be intercepted by the ROM because we're still doing the shadow thing. We haven't worked out how to shut that off yet. We do have an I/O subsystem now, so we can hook that up. We just haven't yet. I'm thinking that working with shadow is going to be something we do along with the test programs. So what I'm thinking for our test programs is they'll have a common prologue, which jumps up to high memory and shuts off shadow and sets up various things that are common. And then we'll have, after that prologue, we'll have whatever the test program is running out of ROM, which now has RAM available. So we can do push and pops on the stack. We can access memory and all that. Maybe we'll start off with known constant values in various registers and so on. The other ones are going to be the same. Let's spot check the last one. So this runs a 5-5 through the E register. And we see the address is 1B, 1C, 1D reads 4. So 1B here, C, D, and then E reads 4. And the location 4 has a 5-5 in it. So weakness here is that we're using the same value here for our, we didn't read anything, but because it appears in the data that we're transferring, there we have it. So we don't see the 5-5 change, but we do see 5-5 being written here to memory. Okay, so temp got 5-5, and it goes out to memory. It's tempting to Z out the temp register, but if I start aggressively moving all of my data words to Z when I'm done with them, that's just going to slow us down. So there we have it. Move to and from the M register is now working, and that took us about an hour and a half, not too bad. Hour and a half, including testing and plotting and all of that. I'll take it. So, did I write good enough comments? Not really. So what I'm going to do is going to come down here where we have to do add comments. Okay, so we got those to-dos. That's for me to do off of camera. The other thing I wanted to do, we have a to-do list here. So to-do, fix comments, add comments where noted. We also want to do common support for a test program in the hex file. And I'm going to add a little text here, shift from RSTN to illegal instructions for SimMagic. So SimMagic codes are just opcodes that cause the simulation to go off and do something without taking over an opcode that the simulated system would actually do something with. And let's actually set that up as a to-do. So the next thing we want to do here is, shift support to do common support manages shadow. And 32K RAM and 2K ROM. And bus. SIG bus on nobody there. So not part of the decoder, but we're going to write the system so that all of the decoder slots that are not directed at anyone, we're going to direct it at a handler, which halts the system by putting it in an infinite wait state. So infinite wait state and terminate the simulation so that we can see what happened. But terminate the simulation in a way that allows the test code to get access back so that we can properly write our timing diagrams. Thank you. There's our to-dos. And our next doc, I-8080, MOV operations are done. So we're going to duplicate this. That. So operations on M are now done. We have a bunch of files there. IMG, I-8080, MOVM, star PNG. Let's turn those into links like this. So turn off that. Okay, so we can see what the text looked like. And this is open file, colon that, close, new line. There we go. Okay, and now if I F6, this brings our diagrams in line. Yep. So are there any irregularities here? I still have the issue that I'm not doing wait states on memory writes. That's going to bug me forever. It really is. Maybe I will figure out a cool solution to it. Maybe I won't. So next step, we have this move immediate, which is our next thing. Let's turn off the diagrams. Yeah, turn off the faultification. So we have this one instruction left called move immediate M, comma, whatever, which is going to have a immediate byte, just like the ALU ops, and it's going to then write it to memory, just like the memory stuff. So this, again, is going to be something that I'm going to implement in source i8080 mov.c. This file is getting longer, but they're all very related, so This is MVI. So move immediate. Let's turn on the PDF again, and I need to remember to turn it off, so let's put it in front of my screen. So move immediate R comma data is a, not R data, M data. We have R data, we now need M data. So we should be putting it in the MVI file. Right. And that actually worked better. MVI is still very short. So we are moving immediate into M. So M1T4 is a nothing. So we're going to compare with MVIR and MVIM. So M1T4 is the same thing, and M2 is the same thing, but we're moving into the temp register. And instead of being the end cycle, we now have an additional cycle out the end, which is out HL. I'm going to move the PDF. Oh, actually, I'm going to let you stare at that PDF for just a moment while I go refill my coffee mug. Okay, next step. So just to quickly review, we are going to be a lot like MVI into a normal register, but where we would normally out here in M2T3 write the data to the register, we're going to accept it into the temp area first, and then we're going to swing into an M3 cycle, which moves the temp area out to memory. Okay, let's turn off the PDF, swing that away. And now we can do this. So, I can just use the same naming here. Like that. So, by doing that, I've now introduced an error that MVI M2T3M is not defined. And that's because we need to do something here. Pound define. Okay. So now we don't want to implement our M register with the macro, but we want it to be very similar. And the name of the function is, come on, Start from there. Grab that whole name. Static void that. We don't send it to R, we send it to TMP, and we are not doing that yet. And we are setting CPU arrow next state next equal to state MVI M3T1. Which means we also need to define this up here. We need a T1 and a T2 and a T3. I'm going to keep the M on the end. So this is going to look a lot like moving something to the M register. So source i8080 mov.c. T4WR. This is going to look a whole lot like these guys. In fact, it's going to look almost exactly like those guys. M2, so MOV M2T1WR gets changed to MVI M3T1M. There will probably be small changes, or maybe there won't be. So this is a case where if we had done all of these in the same thing, we could have reused the same functions. M3T1M. MOV M2T2WR becomes MVI M3T2M, and MOV M2T3WR becomes MVI M3T3M. So this guy puts HL out on the address bus, and it's a memory write. We go down to here, and we release sync, and we put the temp value onto data. And then we come here, and we put the write pulse out. And we're done. So, how are we testing this? I think I need to test this in MVIM. Or MOVM, actually. So MOVM test. We're going to get back in here. We've already incremented this to be at the next byte. So what I'm going to do now is MVI M, AA 055 hex. So we're going to write a 5.5 and an AA on the end. So we get to the bottom of the test. We say else if there we go. Now, if that worked right, we should now have an additional plot which shows MVIM working properly, because we didn't get an error and we are still executing that test, right? So we get back into doc, img. Actually, let's get back into doc. Now I could just put it right in line here. Operations on MVI is going to get moved up. And it's actually MOV M6. So here is the MVI test. The instructions are move M55, move MAA. So our address bus is 21, 22, 5, 23. So 21 is the opcode, and 22 is the data. So we get the data coming on the data bus. Where did the data bus go? Here. 5.5 comes in. Notice 5.5 is not being placed in a register. And we are doing a write with 5.5. And then we do something very similar. The next address, we increment HL to point to 6. And we get an AA as our immediate, and we write the AA value out. And there we go. So that's a nice little picture of the MOV. Now, all these say IO instructions, so I haven't fixed the captions of the tests for MOV. I'm going to consider, for the purposes of the PNG captions, MOV-M will include MVI. Got it. So that was really fast adding MVI in because all the pieces were already there. Now, this would be even faster. I was thinking last night about forth and threaded interpretive languages and indirect threaded interpreted languages and direct threaded interpreted languages and call threaded and so on. Now, all of my little functions that I'm doing here are made up of these little teeny units, which correspond to something happening inside the CPU, some latch going off. So if I was actually to write some microcode, you do this all microcoded. So there would be a microcode, not a VLAW, just a bunch of sequential byte codes. And the byte codes would be things like set M1 or let's see, I-80. Let's take a look at these states. So something like gate a register pair into IDAL. There would be one of those byte codes for each register pair. There would be a byte code for enable IDAL onto adder. There'd be a byte code for set a status word and start sync. There'd be a byte code for stop sync and so on. If I did that, then I would end up building up this library of macro operations that you operate on, go on inside the CPU that are smaller than an opcode but bigger than a C instruction. And then my code here, instead of being a function, I would call this would be a list of byte codes. And the CPU would execute this by executing byte codes until it came to the end of a T state. And the next T state would pick up the list again. It would continue. And would keep doing that, knowing that if we ever raised this return to M1, that would set our microcode pointer to the beginning of the normal thing. I think this is slower. I think this involves more trips to memory. Specifically, it's a byte code that points to a table, and that table has a pointer to a function in it. The other way you could do this is instead of a list of byte codes, you have a list of functions. So instead of having one function to execute for the entire T state, which does a switch, we'd have a function for each one. And then this guy, there would be basically a list of function pointers to call. So you'd call several functions for the T state. Well, we do have a mechanism that does that, and we do know that there's overhead there. Then there's call threaded. So I could take what I'm doing here, and instead of say add or two of this, I could call a support function that says idle from this and so on. So I would then not be writing these specific lines. I would be writing a function call that does a couple of them. So for instance, well, I would have to identify that we would start out with one function for each one of these, but that is, again, even though it's a call instruction inline, and by inline I mean it's likely the compiler would inline it, it's still overhead. Maybe we'll do some refactoring in the end where we start identifying common patterns and turning them into subroutines, and then common lists of subroutines become lists of pointers that we iterate through and so on. And each one of those steps we do might be good to see what performance impact they have. And if that's a clarity impact, so that people reading this down the line, well, once we get this working, at that point we're going to start iterating towards making it a more pedagogical example, I think, if we do more work. It could be that once we get this working, we move on to another simulation. But that's a potential. So what do we want to do now? We are almost 2 hours into the stream. I could do these operations on M, the LU operations on M. How big are files getting? So these LU operations, INR, DCR, are here in, I believe, 8080 ALU, where we have a whole bunch of stuff. And we would be extending this to do the operation on the M register instead. Let's look at that and see if I am up for starting this 2 hours into the stream, or if this is going to be a longer job. This thing, ALU operations on M, may be long enough that we don't want to do it right now. So let's take a look here. We have add R and add M. So the add R in a M1T4, it was setting up the operands here in temp ACT, and then we had the add immediate, which then added in this M2 cycle that read it, and then we had this follow-up that wrote it out. We go to M. Now T4 can set up the accumulator temporary, just like the MVI or the ADI. The M2 cycle now gets the operand from HL rather than PC. Well, that's not hard. And the only difference between the various operations, just kind of like ADI to ACI, the only difference occurred when they did the computation here during the T2 cycle of the next instruction. That doesn't sound like it's going to be hard. So let's see if we can do that in this stream. Turn off the PDF. So we have INR, DCR, add, ADC, sub with borrow, ANA, XRA, RIA, and CMP. Oh, good Lord. This breaks up into two groups. Increment and decrement register are IncDec, and then these are ALU ops. So we'll go first to i8080 inkdeck.c. And now we want to have decodes for M, which are going to exist here, but they are not going to be instantiated by the macros. So increment register, there's going to be a T4 for increment register M, and there's going to be a decrement register for M. Let's get the increment decrement working separately, and then we'll look at the ALU. So let's verify I'm not doing something. I've looked at the ALU ops. Let's look at INR and DCR. INR, so increment to register versus increment memory. Register did all the work in T4, T5. For memory, T4 is going to go out to an M2 cycle, and a M3 cycle to write back. So increment decrement are going to be significant work. I will do them. We're going to be copying a lot of code around, aren't we? Anyway, we do this. I'll do this in the increment decrement area just because it kind of belongs there. But yeah, we're going to have significant duplication of code. So we've got a T4 and a D4 for the decrement register. We do not have a T5 for them. Okay. This also includes INX and DCX, so we could ignore the register pair stuff for now. We now know that this is not going to be null. We can eliminate the variable here. Okay, so these are used but never defined. Fine. Can I get rid of any of these? Turning on the PDF again. So INR M performs its computation here in M2. So we are incrementing data to temp, temp plus 1 to ALU, ALU to data bus. So they can share the M3, which is write to M. Now we start hooking it up. We know that the T4s have been hooked up, but they haven't been written. And the other ones haven't even been macroized out here. Well, not macroized, haven't been set up. So let's put the statics at the bottom. M1 T4. So each one of these needs to be a function. Let's see here. How can I do this efficiently? This becomes a void. And the semicolon expands to, let's do one of them and then use a editor thingy to do the rest of them. There we go. I didn't pick up the parameter list, so it's from here to here. That should sort of compile with the TBD being, yeah, there we go. Now, each case I want the TBD go to the next function down to start with. We'll work that out later. Not actually accurate. That gets a bunch of them. And now we start lacing it up. I need to put in a to-do for the function macro, function comments here. Static void. Boy, I'm just fumbling all around today. Start macro, static, void. Capture that. Try again. Okay, so one at a time now, we step through this and work it out. So M1T4M for this guy. This is increment register, INR. I'm going to go back to the PDF code repeatedly. INRM does nothing except turnover control to M2T1. That's correct. M2T1 is a T1 cycle, which initiates a read from memory, INRM, so reads HL. Where do we have that? We have that in I8080 MOV.c. Look for the read. Where do we set HL? Here we go. So this is the function we want to be very much like. Okay, so we are putting M out because we're going to read M. This is an M read. Boom, boom, boom. And then T2M, M2, T2. We have also an M2. We need a T wait as well. M2, T2. The work there we do is here. T wait. Issues the wait state and does that. T3 needs to do a bunch of things. We do not do it at M1 because we have more work to do in the instruction. Phi2 rising, we are bringing the data in. And in this case, the INR, M, brings the data into the temp register and then into the ALU. Like that. Oh, and we have it undeclared there. So DCR M1 T4M was not declared. Well, M1 T4 should have been declared here. Oh, this is just DCR T4. Okay, so yeah. Back to the top. Do work, do work, do work, do work. M2 T3. Now we're at DCR. So this is the increment register, M2 T3. And then we'll have the decrement register, which is going to look a lot like the increment register. So much like it, I'm going to just wipe these out and replace them. And this is INR DCR M3 T1M. DCRs go away like that. Correct. So decrement register, boom, boom, we read it. T wait, and there, and the difference is all, so we can do -1 there. Okay, no more errors until we get down here. So now we are looking at the third machine cycle for all of these, which is simply a write to memory. So T1, that goes in there. T2, that goes in there. And T3, that goes in there. So INR T4M is never used. Well, it should be in that table. Oh, it's used but never defined. So the problem is I called it something different. Used, never defined, defined but never used. There we go. So the thing is I don't have a T1 in the names here. M1. There. That compiles and runs and reindents, and we are good. So we now have increment memory and decrement memory. And I'm going to again add this to MOV test, where we're going to go back into ASM, MOV test, and RM, and DCRM. Okay. And now, of course, our test condition is going to fail because we need to put in the equals 7, 8. And these are going to be RAM start val +1 and -1. So question, do these INR and DCR of M, do these affect the flags at all? Turn on the PDF. Scroll forward to INR and DCR of the memory. INR M. All flags except carry are affected. So, yeah, there's that. How am I going to test the flag words for this? Or am I even going to test it? Am I just going to wash my hands of it for now? I think I'm just going to wash my hands of it for now. 8080 inkdeck.c. So we had inkdeck flags that we were using. I'm going to make sure that that's at the bottom of the file. So there's my typical usage. So on these guys, where I increment and decrement by 1, flags. Do increment first. The way I was doing this was this. So old is the flag's value. This is the value from the data bus is coming in and goes into the temp register. ALU gets temp +1, AC gets that, and flags get that, and we retire to temp, ALU, and flags. And we have to deassert data bus in and address as well. Same thing here. Whoops. This is in M2T3M. This is -1. So to test this, what I really need to do is increment a range of values in memory. And after each increment, knowing what the source is, the source data is, I would then need to put in conditional branches to test things. I think I'm going to do a proof by programmer examination. Commit temp, commit ALU is done up here. ISOC does not allow nested functions because I duplicated this switch phase. Observed value is 91. Expected value is 91. Observed value was hex 23. Which means that I messed it up when I, oops. So old is flags value, temp is data value, ALU is that, inkjet flags, commit temp, commit ALU, commit flags. And then we go down there where we are sending temp, which means I need to leave my result in temp, not in ALU. Or is that correct? Did I move that up? I think I'm writing from the wrong place. Yes, I am. So we go back to our timing diagram. One more. And turn it on. We see that INR is doing DDD into temp, temp +1 to ALU, and the ALU goes into DDD, and the INR of M. Similarly, it's temp +1 into ALU, and we're writing ALU to the data bus. So I am simply writing the wrong thing at the bottom. The other thing is that I am reading from ROM, incrementing it, and writing to RAM. So because the shadow is still on, right? Shadow is still on. I8080 MOV M test. Oops. So my expected value is not the RAM start val, it is the ROM cells plus 1, because we are reading from the ROM, we are incrementing it and writing it to RAM. And there we go. So that does increment and decrement register. And I think that's as much as I want to get done right now, because the next bit is a lot of instructions, and they are doing arithmetic operations on memory, which means they're going to read from the ROM, do the ALU operation, and write to RAM. Okay, so it's going to be this same pattern here, but I think that's going to be it's going to be a lot more shuffling of data around. So we're going to commit this, and I'm going to do a quick once over to basically put comments in all the places I've done to-dos. We'll push that to GitHub, and we will start a new session with the next instructions. So doc i8080.org. Let's turn off the images. We have done INR and DCR. And this is in MOV 7 and MOV 8 should be here. I should be able to bring it up. Interesting. Right, so I need to go back to my ASM MOVM test. That's not right. Literally, it's doing nothing. Oh, because I didn't wipe them out before I rebuilt it. Right. So it had a plot from the first time we ran with the code where it wasn't working yet. We only have one diagram with both increment register and decrement register. So there's the text, fontified and inlined. And now we can see the ALU 2.3 to 2.4 and D7 to D6. We can see the flags coming through. So the way we check this is for the engineer to examine this by eye and express confidence that with these flags taking on the appropriate values, which he is just going to assert are appropriate because it all just works, that we don't need to do the exhaustive stuff yet. So maybe in the next stream where we start doing ALU operations, we'll break down each one and run things that exercise all the flag bits based on each instruction. That will be a very long, slow sequence. Actually, I'm just going to put this like that. Okay, and that looks right. We've got a couple of memory writes in there. We've got the data. We've got things moving around. We've got the check is working. Yeah. Okay, I will commit this and push it, and then I will add some comments, and I will probably do a amend with the comments, and that's it. So until I see you again, you want to